Good morning, boys and girls, and welcome back. Mr. Mortara here, ready to graph some rational functions with you of like all different types. Okay, basically throwing every trick in the book we have at you guys. So kind of a fun day we have before us here. All right, so let's go ahead and start with a little bit of review because we're going to have to bring in all of our rules when we try to attack rational functions. So to start out with, vertical asymptotes. How do we find vertical asymptotes? And remember, we're going to find vertical asymptotes by setting the denominator or the bottom equal to 0. And you're going to solve that. We're going to go where, again, where that function was undefined. Also, when you do this, be sure that you've already canceled anything out, right? If you can factor and kill things off, that's really the first thing we're going to do. It's just the leftover parts. That's what I'm going to set equal to 0. And that's how I'm going to find my vertical asymptotes. After you find your vertical asymptotes, and remember when you kill things off, that creates a hole. So take those canceled parts and set those equal to 0, and that's how you'll find where your holes are at. All right. Then after you do your holes and your vertical asymptotes, then you're going to look for vertical asymptotes. And to again find vertical asymptotes, you want to look at the degree or the powers on your rational expression. If our rational expression is something in the form of y equals a x to the n over bx to the m, where n and m are the highest powers on the top and the bottom, I really don't care about what comes after them, then we're going to follow these three cases. Case 1, if the degree of the top, or n, is less than m, the degree of the bottom is bigger, the degree of the top is less, then there's a horizontal asymptote at y equals 0. We have dealt with that one a little bit up to this point. Okay. Case 2 is where n equals m. If the degrees are the same of an x squared on top and an x squared on the bottom, then the horizontal asymptote is y equals a over b, where a and b are leading coefficients of the numerator and denominator. So a is the coefficient on top in front of that highest power, and then b is the coefficient on the bottom. And we've done a little bit of case 2. The one we haven't dealt a lot with yet, and we're going to deal with today, though, is case 3. And case 3 is when the degree of the top is greater than the degree of the bottom. All right? I've got an x cubed over an x squared. Okay? And when that happens, the horizontal asymptote does not exist. If the degree of the top is bigger than the degree of the bottom, then there are no horizontal asymptotes. So, degree of the top less than bottom, y equals 0. If they're equal, a over b, where a and b are leading coefficients. Again, don't forget the y equals on those guys. It's not just a number. You need the whole equation. And then case 3, if the top is bigger than the bottom, then there is no horizontal asymptote. Okay, it does not exist. Now, what does happen if the degree of the top is bigger than the bottom is you will get other asymptotes. We are just going to quickly more preview this. We're not going to get crazy into it. As you will, like if you go into trig, pre-calc, or other math classes, but a slant asymptote, okay? A slant asymptote occurs when the degree of the top is exactly 1 more than the degree of the bottom. So a slant asymptote will be a slanted line. You know, think about your normal line. You know, it'll be an asymptote that looks like that. It's been modeled in the form of y equals mx plus b, but it only occurs when the degree of the top is higher by 1 than the degree in the bottom. If the degree in the top was higher by 2, then you would get you might get a quadratic asymptote, okay, a parabola asymptote, and so on and so forth. It's really kind of interesting if you start to play around those. Again, we are not going to get that crazy, but just so you kind of have an idea of where these things kind of lead to, all right? If we want to find the slant asymptote of a function, and again, we're not going to really do a bunch of this, but just if you wanted to, you would do either long or synthetic division. Depending on what kind of polynomial you have on the bottom, if it was like an x plus 1, x minus 1, I would probably use synthetic. But if it's something larger, then you'd have to use long division. And whatever my answer is when I divide the two, that would be the equation of my slant asymptote. All right? So those are the general rules, again, that we are going to keep in mind as we start to play around with our new graphs today. Important to keep these rules in mind because these equations, as we glance at our work for today, they don't look that different from one another. Okay, these equations are fairly similar in our 4 examples. However, you're going to see that these graphs all look incredibly different. All right, so without further ado, let's get to it. All right, so on number 1 here, if I were going to attack this problem, my first step would be to see if I can factor and kill anything off. Can I create a hole anywhere? In this case, x squared plus 1 is the only thing that could possibly be factored. But because that is a plus, I cannot factor x squared plus 1. There's no GCF, and that is not a difference of squares. It's a sum of squares. So no factoring can be done. So that part's done. There are going to be no holes. All right? Then the next thing I would do is I would look for vertical asymptotes. And again, to do that, I'd set the bottom equal to 0. And when I set the bottom equal to 0, I get x squared equals -1, which can't happen. I know that's going to give me an imaginary solution. So there are going to be no vertical asymptotes. And you would want to write none in the line for your vertical asymptotes. Don't just leave that blank on a test because then we think you don't know how to find it, okay? Make sure you let us know that there are no vertical asymptotes. Write none. Okay, and then after I look at vertical asymptotes, I'm going to look at horizontal asymptotes. And so again, I need to think about my 3 cases. Is the degree of the top less than, equal to, or more than the bottom? In this case, the degree of the top is technically 0, since there is no x, so I kind of wrote my own little x there with a little 0 on it. So the degree of the top is 0, and the degree of the bottom is 2. And so therefore, the degree of the top is less than the degree of the bottom. This is case 1, and that tells me I have a horizontal asymptote at y equals 0. We can go ahead and we can draw that in. Now, after doing all this thinking, we said this is when we're going to kind of start to go to our calculator and have it help us a little bit. And we said we wanted to kind of fill out a table, and we wanted to pick values that were near our vertical asymptotes, right? But in this case, I don't have a vertical asymptote. So when this happens, if you don't have a vertical asymptote, you want to pick values that are near the middle. In this case, I would make a table, and I'm going to use the values from -3 to 3. And if a table is not provided for you, I would just sketch one to the side, just like this. And now I'm going to take out my calculator and plug in this function so I can fill out the table from my function. Okay, so quick reminder here, to graph a function, you're going to go to the y equals button, and you're going to type it in here. If you have more than one thing on top or on the bottom, you would better put it in parentheses. But I've typed in my function to my calculator. And then to get the table, we are going to hit second graph. Table right there, second table. And now this will give me the table that I want to just copy on my work. Again, I always tell my students, copy the table onto your work so I can see what you had in your calculator. That way I can, give you partial credit. Maybe you mess up graphing something. I at least know you plugged the right thing into your calculator if I can see what you had on the table. But I'm just going to copy the table from my calculator onto my sheet of paper, and then I'm going to put this away for a second. I don't want to ruin any surprises. Okay, so we'll come back and we'll pull that back out when we're done. We'll see if our graph matches what the calculator says it should. Now we're going to go graph these points. Left 3 up a half, left 2 up 1, left 1 up 2.5, 0. I'm going to go up 1, 2, 3, 4, 5. I'm going to just put all my points on the graph where they belong. Once all your points are graphed, then you can go ahead and sketch your picture. You should have a pretty good idea of what it looks like, but if not, again, you can always look at your calculator to get an idea at this point, I would say. All right, and here's what I think we're going to get, and I'm going to check it on the calculator. Oh, okay, if we look at the calculator, I think we did a pretty darn good job. Moving on to number 2. Okay, on number 2 again, the very first step is to factor and try to kill something off. In this case, we could factor, because it's the difference of squares, but I'm unable to kill anything off. So we're going to set the bottom equal to 0, and we get, actually in this case, 2 asymptotes. Before we've only had 1, but now we've got 2. One's going to be at +2, one's going to be at -2, and you could write this as x equals plus or minus 2. Asymptotes are always going to be dotted lines, just like that. And again, I'm going to put them at plus and -2 on the x-axis, and then we can talk about horizontal asymptotes. In this case, again, the degree of the top is less than the degree of the bottom like last time. So we're looking at case 2, and so my horizontal asymptote will be at y equals 0. Once we've thought it through and done the heavy lifting, now we're ready to create a table of values near our, again, vertical asymptotes. And we're going to use our calculator to get those values to help us graph the function. All right, but again, you always want to go near the vertical asymptotes. In this case, these are the values that I would pick. I like to do at least one value. In this case, I did 2 on the outsides of my asymptotes. So like at -3, -4, and +4. And then I generally want 3 values on the inside between the 2 asymptotes. So in this case, I chose -1, 0, and 1. -2 and 2 are my asymptotes are at, and I put little lines next to them to remind me that those are where the asymptotes occur at, so I shouldn't have values there. Now I'm going to use my calculator. I always type in the original problem into the calculator. That way, even if I mess something up down below in all of our other work, what I'm going to graph should be right as long as it matches what I have on the calculator. And then I'm going to go to the table. When you're copying your table to the graph, a couple things. Again, you can move up and down if you have to by using the up and down buttons. But you're going to round to the nearest tenth. Okay, that's about as accurate as you need to be. And anywhere where you see, again, error, that should be a place like we have an asymptote. So that just helps me to make sure I've got things set up correctly. Again, looking at my calculator, I slid down a little bit here to grab the last few values. Again, I'm just going to round to the nearest tenth. And when you do this, you should also notice that you probably are going to get some symmetry in your graphs. That is normal and should make you feel good like you're doing it right. Once we have the table filled in, we can go ahead and graph these values. When you're graphing in these dots, again, it's kind of hard to see. They're going to be close together. I try to exaggerate. Again, we're sketching, so I just try to exaggerate with that a little bit so I can get a feel for where the graph is going. And then I'm going to look at my calculator to help me graph the rest. I'm going to approach the asymptotes but not cross them. I think this graph should look something kind of like this. And double checking on the calculator, I think that looks pretty good. I think we're pretty close. Okay, on to number 3. First step, try to factor and cancel. In this case, we get 3x over x times x minus 1, so I can cancel off my x's. When I cancel off those x's, that creates a hole. Set what you killed off equal to 0, so at x equals 0, I've got a hole. And now look, if I look at the remaining equation, hey, that's in my HK form. Awesome, I don't have to use those other rules. We can use the shortcut trick of HK. This is going to shift right 1 and up 1. So now I'm going to go and put my asymptotes in. So we have a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 1. In this case, I would say we are not using the cases because we're using HK form to graph. So you could leave that blank, but I would communicate with your teacher that you moved it right 1 and up 1. I think that's an important piece of this. If you wanted to use the case, you would need to get the common denominator of the 1 and the x minus 1, and you'd want to put these together to create one fraction. Then you could use your cases. If you chose to do that, you should get something like y equals x plus 2 over x minus 1. And so we would be using case 2 since the degrees are the same. At this point in time, you could either create a table with values near 1 and use your calculator, or you could use your a value and use the trick with the a value to make sure that you're graphing in the right spot. I think it's easier to graph out HK when I can, so I'm going to just use my a value. So to graph this, I would go to the right 1 and up 3 from that new intersection, and to the left 1 and down 3, and then I can sketch my graphs between these two asymptotes. And just try to sketch a nice smooth curve as best you can. A little bit hard for me here. My bottom one is not as curved as I'd like, but we'll call it good. It's good enough right now. When you're all said and done, just don't forget, if you have a hole, you need to go and create that hole in your graph. And you're just going to do that by erasing a little piece and drawing in the hole. And there we go. That's what this graph should look like. Again, when you're done, you can always check yourself on the calculator. When you do this, always plug in the original function. And I would say in this case, again, we are looking pretty good. You will never see a hole on your calculator, only if you go to the table where you see that the hole is there, and it'll say error. All right, boys and girls, one last one. Okay, step 1 again, on number 4. Factor and try to kill stuff off. In this case, we have an easy trinomial, and it factors to x minus 1 times x minus 1, and I can kill off one of the x minus 1s. Take that piece that you killed off, set it equal to 0, and then now your hole is at x equals 1. We are left with now y equals x minus 1, which for us is good news because this is not even a rational function anymore. This is just a line, y equals mx plus b. So there are going to be no vertical asymptotes nor horizontal asymptotes. There are no cases to deal with. And I'm just going to graph this line. If I did have to state a case for this, though, going back to the original, because the degree of the top is bigger than the bottom, I would say that this is case 3. Graphing this like normal, this has a y-intercept of -1, and it has a slope of 1. So I put my points where they belong there on my graph. And now I'm just going to sketch in my hole and the rest of the function. We have a hole at x equals 1, and there it is, boys and girls. That is what this function looked like. 4 different graphs They look all, equations similar, but they all look very, very different. See ya!